We present ASID, Active Exploration for System Identification in Robotic Manipulation. Solving dynamic tasks via sim-to-real transfer is hard, because we don't know the underlying physics parameters of the real world, like friction, damping coefficients, or inertia. For example, if you want to stack objects, we require precise information about their center of mass. Otherwise, they will drop when we attempt to balance them on one another. Or when playing shuffleboard, we require knowledge about the surface friction to perform a precise shot. We present ASID, a generic pipeline for sim-to-real transfer that can solve those dynamic tasks in a zero-shot fashion. Consider a dynamic stacking task, where the goal is to balance a rod on a tower. The center of mass, here indicated by a blue marker, is unknown to the robot. During test time, the robot must therefore identify this property to successfully solve the task. We consider a sim-to-real setting where we synthesize control policies in simulation and transfer them back to the real world to solve the task. Simulation not only provides us with infinite cheap data, but also gives us full control over the data generation and policy learning process. For example, we can train a policy over multiple poses and center of mass configurations of the rod. The result is a policy that solves possibly infinite configurations of the task. This technique is commonly referred to as domain randomization. Let's see what happens when we transfer such a policy back to the real world. As we can already see, the policy trained with domain randomization fails catastrophically because it tries to learn a policy that works for all possible configurations seen in simulation. It therefore converges to an arbitrary action that does not solve the task in the real world. On the other hand, our policy first explores the real world and identifies the correct center of mass. It then targets the simulation training towards a single configuration that accurately represents the real world, which allows for zero-shot transfer of the task policy. Our key insight is that transferring dynamic tasks from simulation to the real world inevitably requires real-world exploration to solve the task. Separating the exploration and task, ASID first trains an exploration policy in simulation using a Fisher information-based objective, while a policy trained in sim to accomplish the goal task might not effectively transfer. Strategies that explore effectively in sim often transfer pretty well to the real world. And indeed, the transferred policy pushes the rod and gathers sufficient information data. Feeding the collected data into a system identification process then bridges the gap between sim and real and lets our system create a high-fidelity simulation. Training in this updated simulation then allows for zero-shot transfer of the learned policy to the real world. Let's see how our method compares to domain randomization when exposed to different center of masses and rod poses. As expected, domain randomization converges to a single action that is most likely to solve the task in simulation, but fails to solve the task in the real world. ASID, on the other hand, correctly identifies the center of mass and trains a policy that solves the task. It only fails when exploration data is ambiguous and the center of mass cannot be identified correctly. We further evaluate ASID on a shuffleboard task, where the goal is to shoot the puck to either the yellow or the blue target zone. Because every shot changes the surface friction of the board by redistributing the sand, re-identifying the surface friction before every shot is crucial. While domain randomization shows some success when shooting the puck to the yellow zone, it completely fails to target the further away blue zone. Let me leave you now with a short summary. We present ASID, a sim-to-real framework that decouples exploration and solving the task. To effectively explore the sim-to-real gap, we introduce an objective based on the Fisher information that seeks out trajectories that are most sensitive to the underlying physics parameters. Thanks for staying with me, and have a look at our website for more cool videos.